I want to start with just answering the question why I am here. I'm a developer, software developer. My background is probably rather unusual in that my first job coming out of university was doing functional programming in Haskell. How many of you are familiar with Haskell or functional programming in general? A couple of you, okay, excellent. How many are doing programming on a regular basis? That's another question. It's almost all of you, okay, good. Otherwise you wouldn't get much of this. So, my experience was that I got to work with the functional programming for quite a while. Then I got a job doing development in C++ instead. So I got a chance to learn how to use object-oriented modeling to a larger extent. And got to learn all the neat tricks there. Then I got to work at Click. And at Click, I got to work with C#. And I started working with C#, I noticed that I could use a lot of the things I learned from functional programming also in that language. And I also noticed that the style I was writing my code in was, in many cases, a little different from what my colleagues would write. So I ended up thinking that maybe it would be a good idea to give a little presentation on Haskell and functional programming to sort of explain where I'm coming from. And that's sort of the source of this presentation here. So in the original presentation, I gave an introduction to Haskell. I've scaled down that quite a lot here to make it fit into 4 to 5 minutes. But the first thing I'm going to do is to have a little look at this little construct. So the for loop. The first thing you see here is a for loop as it would have been written in C. This is C language, right? You have an index value that you increment and you loop across this set of customer names. You want to print those to the command line. That's sort of the basic way you would do iteration across a vector. When I got to work with C++, I would write a lot of these for loops instead. I was using iterators back then. And the big difference here is that this construct here, the iterator, are everybody familiar with what an iterator is? Most of you? Okay, good. So the good thing about this is that it sort of abstracts away many of the features of what I'm trying to move across. Here it has to be a vector. If I were to move to some form of different construct here, like a list, that will have forced me to rewrite this altogether. But with this iterator construct, I don't care if it's a vector or a list or any other construct, that as long as it supports this iteration operation. And another important thing is that when I use this type of pattern, this type of programming pattern, I know that people who will read this code can recognize these iterators and immediately know what they're supposed to do. Once you see an iterator, you know that this is something that moves across a set of values, basically. Now, another way to write a for loop is this. We're using a for each statement. And most modern languages now has this type of construct. When I was doing C++, we didn't. So that's why mainly we resort to this. But for each is very nice, because this sort of abstracts away the whole thing of how you move across a set. This is sort of baked into the statement itself. So it hides a lot of the details of how you're trying to do something, and instead of focusing on what you're actually doing. Actually, it's very, very rare that I write any of these kinds of loop now, because this is almost always what I want. I want to move across a set of values, and I want to do some form of operation of all of them. Well, the last way to write this is this one. And this is where my new experience from Click comes in. Because here, what I'm doing instead is using what is more or less a functional pattern. Instead of iterating explicitly across some set of values, I just say that I have a function, and I want to apply that to all the values of this set. And this is what this talk is going to focus on, this type of pattern, functional patterns for dealing with your data, basically. So, I'm not going to give a big introduction to Haskell today, but I will give you some insights, because most of the presentation from now on will be based on Haskell. So, I will start by writing a very simple function in Haskell. It's a function that summarizes a list of integers, and this is how you would in Haskell write a type declaration. So sumInt is a function that takes a list of integers and returns an integer that is a sum of all of these values. And one way to write this in Haskell and implement this is by using recursion. You would never use a for loop in Haskell, basically, because they don't exist in Haskell. But recursion is something you would resort to quite often. And also another thing you can do in Haskell is to do pattern matching on arguments to a function. So what you see here is a function that defines 2 different cases for its argument. The first one here is the empty list. And if I want to apply sumInts to the empty list, what I should get is 0. The sum of no elements is 0, right? And here, I pattern match on a value on a list that has at least one element. And if I have a list that has at least one element, well, then I want to take the first element, and I want to summarize that with what I get when I summarize the rest of the list. Everybody agree on that? Do you feel comfortable with recursion? Yeah? Excellent. So, another function we could write is a function that concatenates strings. So this has a sort of similar type signature here. I take a list of strings, and I return a string that is just the concatenation of all of them. And if I were to implement this using recursion, it will be very similar. So for the base case, for the empty list, I just want to return the empty string. For the recursive case, I will pattern match again on the list that has at least one element. And in that case, I want to take the first element and concatenate that with what I get when I do a concatenation of the rest of the list. This is the operator in Haskell that does concatenation of strings, by the way. So, now, when we look at these two functions, we can see that they are very similar to each other. They have very similar structure in how they are built. The different types, the different some functions, but we can see that they are sort of in the same family. Actually, if we try to identify what the common patterns of this is, we can list them in three different things. First of all, there is a function that takes two values and combines them into one. In this first function here, we have a plus. Here, we have the concatenation operation. Secondly, there is a base case. This is the value we will resort to when we try to perform this operation on the empty list. And third, there is a list of values. So why don't we try to write a function that tries to capture this aspect of what we're doing? And we will call that the fold pattern. So the idea is to write some function that takes all of these aspects as arguments and tries to apply this function and fold the whole list into this one single element. So the signature for this function would look like this. Here I've turned to lowercase letters here, and that is important because in Haskell, a lowercase letter for a type means that it's a type variable, not a concrete type. So this can actually be applied to any type, as long as all of these types are the same. So the first argument to fold will be this function. So this will be a higher order function that takes this one for the concatenation operation, two arguments, and returns a combination of those two. Second argument is a base case. That's this one in this case. The third argument is a list of values. What we end up with is this folding of the whole list. And if we implement this, we can sort of use the pattern we see up here as well. The only difference is that this here will become an argument. So we have three arguments here now. This is the list that we always had. And for the base case, when we do this on the empty list, we just want to return what the base case value is. We don't care what the function is here. And this is some nice syntax that Haskell has, that if you don't care what a value of an argument is, you can just use this wildcard here to actually say that. And in the recursive case, we will assign a name to this function, and then we'll just pass that on. We will apply this function to the first element of the list and to what we get when we fold the rest of the list. All right, everybody agree on that? So now that you have this function, we can implement concatenate like this. So instead of doing recursion here, we use this fold pattern. So to concatenate a list of strings, that is the same as doing a fold using the concatenation operator and the empty string as a base case. But we can also use this on a lot of other types. So for instance, the sum ints can be implemented like this as well. So if we want to do sum on a list of values, we use the plus operation, 0 as the base case. If we want to do a product, multiply all the values, we pass the multiplication operator and 1 as the base case. Or we could do this on booleans. So if we want to do AND on a list of booleans, we can use the AND operator and true as the base case. This is a real flexible thing. And actually, if we step back and look at what we've done here, what we have done is to sort of capture a common case of how you will traverse a set of values and built that once and for all so that we can, when we write this, we can focus on what is the really important thing of the implementation. And in Haskell, you have a lot of these patterns. So this is a list of some of the most commonly used. Map is probably one that you use the most. Map takes a function that takes an argument and returns some value and applies that function to all the values of the list. So here you see it's two different variables here. That means that you can return a different value than you got in, right? But these have to be the same, so this is the same as this. Filter takes a predicate or a function that returns a Boolean and applies that to this list and filters out only those values that satisfy this function. Take while will take all the elements of this until this predicate returns false, and it will stop. All and any will apply this to all these values and return true if all of them were true or at least one of them were true. Zip with takes a function that takes two arguments and two lists. And then it does a pairwise application of this function on all the elements of the list. So it will first apply this to element 0 of this and element 0 of that and return a value of type C. Then we'll take element 1 from both and apply that until it reaches the end of the shortest one, and then it will stop. Iterate is sort of an interesting function as well. This takes a function from A to A, it's the same type, and a starting point, and then it produces a list where it just applies the same function over and over again. So the first element will be this value, straight off. Second element will be this value with this function applied once. Third element will be this value with this function applied thrice, and so on. I'll illustrate how these can be used later on. And then we have the folds. This is what we just wrote. Actually, in Haskell, you have two different kinds of these. Fold R and fold L, which actually differ in how they are folding across the list. Fold R starts at the right end, fold L starts at the left end. There can be a difference in some cases. You can also see it has a little more general type declaration than what I showed you. And if you look at it more in detail, you can see that you actually can loosen the constraints there a little. So, and this is what I saw when I was starting to use C#, that I could actually utilize a lot of these constructs also there. Because in many of the modern languages, you will see that this is an aspect from functional programming that has been lifted into other languages as well. In C#, you have the concept of link that more or less provides this straight off. It was used in 2007. In Java, there's a class called Java util stream. Was introduced last year, if I'm not incorrect, in Java 8. And you can see that you have functions that map directly to what you have in Haskell. So the map function in Haskell is called select in C#. It's a member function that you can apply to this set. It takes a function as an argument and does exactly what map does. In Java, it's also called map. Take while I couldn't find in Java, but you have it in C#. This iterate function doesn't exist in C#, but you'll find it in Java. So there are some discrepancies, but if you ever miss some of these, I'm sure you could implement them yourself if you want to. The fold function is called aggregate in C#. It's called reduce in Java, but it does the same thing. It looks like both of them are doing the fold L thing, but could be settings for that I'm not aware of. So, any questions on this so far? No? So what I'm going to do, yes?
Under the hood in C# and Java, it's also recursion, right? It's recursion.
The implementation under the hood here, I'm not aware of how it's actually implemented. I just see what the tools are available for me. Yeah. So what I'm going to do for the rest of this talk is to do a case study where I try to solve a problem that is sort of non-trivial, but not too big either, that illustrates how these functions can be used. And the problem I'm going to solve is this one, the 8 queens problem. How many of you are familiar with that problem? It's 1, 2. Have you solved it yourselves sometime?
No, I watched you solve it.
Okay, all right. That's cheating. Okay, so the 8 queens problem is this. You have a chessboard, and you have 8 queens, and you want to place those 8 queens on the chessboard so that no 2 of them threaten each other. is actually rather difficult. You can go home later on and try to do that, and you can see that it's non-trivial to do that. So we're going to write a program that does this for us. And the reason why I chose this problem when I was doing this talk was that when I had this C++ development position, I had a colleague that was interested in Haskell and thought about, hey, I want to take a look at that and see what I can do with that. And he started with this problem. He wanted to solve this problem in Haskell. And the first thing he did was to start thinking about how do I model a chessboard? Well, a natural way to do that is to have a two-dimensional array, 8 by 8. And I want to have a class that performs that, and I want to understand what functions do I need in order to solve that. And his first question to me was, how do I write an array in Haskell? And the answer is you probably don't. You can't have arrays in Haskell, at least not in a very convenient way. You can use list for it, but you will not have this constant lookup time that you expect from an array. So we talked about this a little, and I went back later in the evening, and I actually wrote a solution for this. That is more or less what you're going to see today. And it has a very, very functional approach, much more than what you would do if you were working on arrays. So I think it's a good illustration. So first thing question I would ask was, what should a solution look like? And there's one thing I immediately know about this problem, and that is that you can only have one queen in each column. It's pretty obvious from the whole aspect of how these queens move. So why don't I have as a solution a list that just denotes what rows the different queens are on each column? So I would do something like this. The signature of a solution is a list of ints. And in this specific solution, the list would be 3, 1, 6, 2, 5, 7, 4, 0. All right. So my strategy would be to use some form of greedy algorithm. So I just want to create all solutions and then take the first I find. My starting point will be the empty solution. So I start off with a solution where I have no queens placed on the board, and then I gradually extend this solution until I get to a point where I have 8 queens on the board. And then I can start thinking about what kind of functions will I need to solve this problem. Well, I need a function that is able to take an incomplete solution or a partial solution and create all possible extensions from that solution. So let's start to look at this function, what that will actually imply. Well, imagine that we have this partial solution here. There are 3 queens on the board, 7, 4, 0. And we want to see what are the possible solutions where we have placed something here. So we just take all of them. There are 8 different positions to have the queens on this column. And then we start to chew them off. So we check the first one. Is it OK to add this one, row 0? And we can check, yes, it doesn't hit anything here, doesn't threaten anything there. But this one, it will hit. So this is not OK, so we remove that. Then we'll take the next one. This one is OK to add up. It is OK to add level. And it's OK to add down. So that one we keep. That's a possible extension. Then we move to the next one. And this is not OK to add, because it threatens this. And so on. This threatens this. And then we end up with just these 2 possible extensions. So all the possible extensions for 740 are 1740 and 5740. Now we immediately see that we need some form of function that is able to do this logic. It needs to be able to take a candidate position for a queen and a partial solution and return either true or false depending on whether it's OK to add. So let's start to look at that one. OK to add takes a queen position and a partial solution and returns a Boolean. So this should return false if you try to add 0 here, like we saw, and this should return true. Now, this can be split into 3 different cases, so we can do sort of a divide and conquer on this. So if you have these 3 functions, OK to add up, OK to add down, and OK to add level, then we can use these 3 to combine them like this. So it is OK to add a certain queen to a partial solution. if all of these three return true. So let's start to look at the first one here, OK to add up. How do we implement that? Well, my strategy would be like this. I have a queen here at a certain position. So let's create this diagonal here, these three values, by traversing up across the chessboard. I start up from 1. 1 plus 1, when I move one step, is 2. 2 plus 1 is 3. 3 plus 1 is 4. And I end up with this list indicating what the row numbers are on the diagonal up. And why would I want to do that? Well, once I have this, it's very easy to check whether or not it is OK to add it up or not, because I can use a pattern. I want to do a pairwise comparison between this diagonal and my partial solution. And that is a pattern called zip-with. I'll come back to this. So basically, I've reduced this whole function to a pattern where I want to compare this list to this list pairwise. So there are actually two different patterns I'm going to use here. First of all, I want to create the diagonal up. And this is basically the pattern of doing iterate. I want to add 1 for every step and create this list. So I can do something like this. If I iterate the successor function, this sort of fancy name for doing +1 on integers, but you could use it on characters, for instance. The successor of A would be B, for instance. But if I do this, I will get this actually infinite list, which is a sort of an interesting topic in Haskell as well. I'm not going to talk too much about. But this will create an infinite list starting from 1 and just incrementing all the time. And the second pattern I would need is this zip-with to do pairwise comparison. Zip-with, I mentioned that earlier, takes 3 arguments. First one is a function taking 2 arguments, and the 2 others are lists, and it will apply this function pairwise on the elements of the list, which is exactly what I want here. So if I do zip-with and then the non-equality operator here, and then this list with just 2 counting upwards, and I zip that with this one, my partial solution, then I'll end up with true, 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 because 7 differs from 2, 4 differs from 3, and 0 differs from 4. So if I combine these 2 patterns, I will get this implementation. So let me just repeat what this actually reads. Here, I'm creating a diagonal. I'm iterating the successor function on my queen position. This creates a diagonal. Then I'm doing tail on this. And that is to remove this first element, which is the queen position itself. Once I have that, I do a zip-with, non-equality, and my partial solution. And finally, I use this AND function, which takes a list of booleans and returns true if all of the elements of the list are true. So AND applied to this one would return true. And that's it. So then we have the implementation for OK to add up. Next step would be to do the same thing for OK to add down. And that is actually very easy once we have this implementation. Because the only thing that differs between OK to add up and OK to add down is this one. OK to add down can be expressed like this. Instead of using a successor function, we would use a predecessor function, which will create the diagonal down instead. So now when I see a case like this, I have 2 functions that are almost identical except for one value, then I would usually create some function that instead captures this value. Yes?
Could you please tell more words about this operators?
This is inequality.
Inequality.
Yeah, so exclamation equals is a common notation in other languages. So why don't we create a higher order function for this? Let's write a function that takes this function as an argument. And I call that OK to add given dir, or direction. And it will be almost identical to what we had here, except for this argument, which are tied to f here, and then use that in the iterate operation. Because now I can write my OK to add up and OK to add down like this. And now we have one function more to write for these OK to add in a certain direction. That is the OK to add level. And this can also be written using this function. What is the function we want to apply to the row position when you want to check on the same row? Can anyone see that? You're not allowed to answer. What? Plus 0, exactly. We want the identity function. The identity function here is a function that takes a value and returns that value. It doesn't do anything. And this is sort of a curious function. The first time you see it, you will think, why would I ever want to use that? But when you start working with functions as arguments like this, you actually end up with using it quite a lot. It's very useful. It's just like doing plus 0 or multiplying by 1. Why would ever you want to do that? Well, sometimes, for instance, you return a value from a function that you want to multiply with something. And then you want to sometimes multiply by 1. So now that we have these three different implementations, we can return to our function OK to add. We wrote it like this previously. So we had these three different cases. Now we can simply replace them by doing this. We don't need those specific implementation anymore. We already have this nice pattern here that we have created. And we pass these three functions in like this. So now we have reduced this OK to add function to simply apply this function here 3 times to these. But that is actually a pattern in itself. So we can take this one step further. Because once we have this, we can take these 3 functions and extract them to a list. We can have a list of functions, which is fine to do in a functional language, and also in C#, by the way. And if we have that list, then this function here is simply a matter of applying this predicate and check if it's true for all these values. And that is the pattern all. All takes a function and a list and returns true if all these values in the list returns true for this function. So if I do all even on 2, 4, 6, I will get true. And if I use that function, I can write my OK to add like this. So OK to add a queen and a partridge solution is true if this predicate is true for all of these functions. All right. So how far have we come now? So this is the current solution so far. We have 2 functions. We have this OK to add given direction that we used to implement this OK to add given direction. OK to add. And now we want to use this function OK to add in order to extend our solution. So now we continue with the problem basically here. And what do we want to do when we extend the solution? Well, we want to take a partial solution and we want to find all possible ways to extend that solution with 1 queen. That's where we start from basically. So extend solution should have this signature. Takes a partial solution and returns a list of partial solutions. And there are 3 steps for doing this. First step is to create all the possible queen positions that we can have for the first row. There are 8 positions, right? 0 through 7 in my case. So you want to be able to create that. Second, we want to take only the queens that are OK to add. So here we can immediately see that this is where we're going to use the predicate we wrote in the previous exercise. Can anyone see what pattern this would be? Not yet? Okay, I'll come back to that. And 3, we want to create extensions based on queens that are OK to add. So for all of the queens that we get from this step, we want to create a new partial solution with that queen added. So, creating all 8 possible queen positions is very easy to do. We just type like this. This is how you do that in the Haskell, basically. This is an expression that we enumerate all the values from 0 up through 7. Next step is to take only the queens that are OK to add. Well, that is pattern filter. We want to perform a filter giving this predicate. So if I do filter even on this value 0 through 7, I will get 0, 2, 4, 6. And then finally, I want to create the extensions based on queens that are OK to add. And that is map. Map take a function. In our case, the function would be to take a queen and append that to our partial solution. And the list of values would be the queens that are OK to add. So map here is an example. If I do multiplication by 2 on 1, 2, 3, I will get 2, 4, 6, right? And if I use these two patterns, I would end up with this implementation. So extend solution takes a partial solution and returns me a list of all the possible extensions to that solution. And it will take a partial solution here. And first of all, I create my 8 different potential queen position. I filter using my predicate, OK to add. Only want those that are OK to add to the queens. And then finally, I map this function, which takes a value and appends it to my partial solution. Everybody follows this? This dollar sign here, by the way, where did I have that? This is just a convenient way to avoiding some parentheses. It's actually a function application. This is a function itself. It's a function that takes a function and a value and applies the argument function to the value. It's also a sort of a strange thing. But when you're working with functions again, that's sometimes useful. Here is convenient because it just takes everything there and applies it to everything here.
The ticks.
Oh, this is to make it infix annotation. So this is actually the second argument to this. So it's a convenient way to just assign it to the second argument. All right, so now we have a function that extends a solution. The next step would be to actually use this. So let's just look at how this should be performed. So this is what I would get if I apply extend solutions to the starting point I had, namely the empty solution. What I would get then is all the different ways I can have placed one queen on the board, which is, of course, all the different 8 positions. Then I would apply extend solution again on all of the values I got here and get a list of lists of potential solutions. So for the first argument, I will get 2, 0. I can add a queen to 2, but I can't add it to 1 or 0 because it will come in conflict with this one. Down to 7, and then I have this large list of lists, and I just want to merge them into one, like this. So here I will have now all the possible extensions to the solutions I got from this one. And then I just want to iterate like this. So I want to repeat these two here. Step 2, step 3, until I get to a point where I have 8 solutions, 8 queens in my solution. So let's do a recursive implementation of this. So all solutions is now a function that takes an int representing how many queens we want to place on the board and returns me all the possible ways to place those queens. The base case will be when I have 0. So all solutions applied to 0 is exactly one solution, where I place 0 queens on the board, in the empty list. And the recursive case, here I will want to create all solutions with n-1 queens, and then extend all of them. So actually creating the solutions for n-1 queens is just applying this function like this. Next step would be to extend them. Then I map extend solution on what I get when I create all the solutions for n-1 queens. And then finally, I want to concatenate them. So this gives me a list of lists, right? And I want to just combine them into one big list. So I apply concat like this, or I can use the concat map, which is a combination of these two. It's quite a common expression that you will do this. So there's a specific function for that. In C# it's called select many instead of select. So there we go. So my all solution functions now can be written like this. However, this is also a pattern here, sort of hiding under the hood. Because what I'm doing is I'm applying the same function over and over again. And that is basically the pattern iterate. Iterate does exactly that. It applies the same function over and over again. However, it creates a list of them. So I want to use this function now to express this instead. Then I can simply write like this. So iterate now takes this concat map extend solution function and applies that over and over again to the starting point there, the empty list. So this will, the first element of the result here would be the empty solution itself. Second element would be a list with all possible solutions where I have one queen. Next element with all possible solutions with 2 queens and so on. So now I just need to take number 8, or number n in my case. That I can do like this. So this is sort of indexing in the list. It will take the nth value of that list. So then I end up with this implementation. All solutions takes a value, indicating how many queens I want to add, and returns all the possible solutions to that. It's simply a matter of iterating on this and taking the nth value. So now we're almost done. We only need to wrap this up. So we now have a function that returns all solutions for n queens. So we just want to take all solutions for 8 queens and take the first. And that you can implement like this. So we apply all solutions to 8, and then we return the first. And we're done. So the full solution we end up with is this. How many are surprised at how short that is? 1, 2, okay, some of you. I am surprised. I'm always very happy when I come to this because it feels like all the code just boiled away. And there's a reason for why it's very short. And that is that I have been using these patterns that are sort of well known and captures all the sort of the gore details of what I want to do. So I can focus on what I want to do, not how I want to do them. Because all of that is already taken care of. And there's another big advantage of using all these patterns. And that is when I use them and someone else comes and reads this code. I'm sure to many of you this will be very, very difficult to read. Yes. What's that?
And difficult to debug.
Difficult to debug. Well, it depends on what level you want to debug it. But I find that when I'm able to communicate using these functions with my colleagues and say that, hey, we want to solve this problem. Okay, why don't you just do a zip? Just like we are sort of used to using our object-oriented patterns. If I say to you that I'm using an iterator, you all immediately know what I mean. Or if I use a factory pattern, you all have a pretty good idea what that means. In the same way, these functional patterns are sort of lightweight ways of dealing with data sets and hiding all the gory details of how that is done. So I find this very, very useful. And that's why also I use this link layer in C# quite a lot. I think I have some time left, right? I can give a quick demo of this. So let's see. So this is the solution written up just in Emacs. Actually, I've done a minor modification. This no longer takes value as an argument. Instead, it just returns an infinite list. And I'll do the indexing here. And if I run this, let's see. Where did I put that? Here we go. So I'm now running this in a Haskell interpreter. And I can now type solution. And I will get my solution. What's that?
If you type it again, it will be the same?
It will be the same, yes. And I can also do things like this. If I do all solutions, let's see. Here, I will get all the possible solutions with 8 queens. And I can also do things like asking how many solutions are there. I can ask for the length of this, and I can see there are 92 solutions with 8 queens. And I can go even further and say, okay, how many solutions are there for the first 10 values? Well, why don't I map length on them? And then take 10. Now we can see a nice set of values indicating how many solutions there are for the different number of queens to add. And I can also use zip now to get this indexing. So here I can now see that it peaks at 5. For 5 queens, there are 568 potential 568 solutions. If someone here are good at math, you can possibly write some formula to denote this. But all right. Any questions? That's basically it.